All right, the next section is inverse relations. We've already looked at this in the past, and just to review, to find the inverse of a relation, you switch the independent and dependent variables and solve again for the dependent variable, meaning you switch x and y and solve for y. Let's go over this by doing some questions. Number one, recall that the volume of a sphere is given by the relationship v equals 4 over 3 pi r cubed. Determine the equation of the inverse. I want to go over in this case to, if we were to switch v and r, the new relationship would look like this. R equals 4 over 3 pi v cubed. But we cannot do that. You cannot switch v and r because now r, which is supposed to represent radius, is actually the equation for volume. So because of that, r represents something different now. So you cannot take this process. In this situation, what we're actually going to do is we're just going to have to isolate for r within our equation. So 4 over 3 pi r cubed, we take pi to the other side, and it'd be v over pi is equal to 4 over 3 r cubed. Take 4 over 3 to the other side and multiply by the reciprocal. So I have 3v over 4 pi is equal to r cubed. Finally, take the cube over to the other side. Requires doing the cube root. So our final equation would be r is the cube root of 3v over 4 pi. That's your process for finding the inverse. Remember, we have to keep track of what the variables represent, because if you switch their spots, they now represent something different. Let's go to our second example. So you're given f at x is equal to x squared. Find the inverse relation. So let's look at A. To find the inverse to f at x, I'm just going to rewrite it as y equals x squared. We switch x and y, so it becomes x equals y squared. In order to isolate y, I'm going to take square to the other side and square root. So that would be y is equal to the square root of x. Remembering anytime you take the square root, we need to have positive and negative in front of it. So y equals positive negative root x would be the inverse relation. And to write it in function notation, so if f at x is x squared, the inverse is written as f inverse x is equal to positive negative root x. Let's go to B. Compare the domain and range of the function and its inverse. To do this, I'm going to include the graphs so that we can understand what we're looking at. So f at x, which is x squared, would look something like that. And we're just making sketches right now. And the inverse of that would be the positive root x graph and the negative root x. So it's just the same parabola, just been reflected over y equals x. So let's look at domain. Domain for this function is xer. The range for this function would be y is a member of the real numbers such that y has to be greater than or equal to 0. And if we look at this function, the domain is going to be that x is a member of the real numbers such that x is greater than or equal to 0. And the range, because it goes up and down, the range would simply be that y is a member of the real numbers. Now to compare the domain and range, we recognize that the domain of the original has become the range of the inverse, and the range of the original has become the domain of the inverse. So they have basically switched spots, which makes sense because in order to go from the original to the inverse, the x and y switch spots. So whatever the y values were in the original, now they become the x values for the inverse. So the x value of the original, which is what your domain is made up of, is now going to be the y value of your inverse, which is what your range is now made up of. Now for part C, determine if the inverse relation is also a function. The easiest way to look at that is using the vertical line test that we talked about in 1.1. Let's get this set up so that it's at 90 degrees. Now, as you can see, the inverse is not a function because it passes through our ruler at two separate points. Therefore, it does not pass the vertical line test, so it's not a function. To determine if the inverse will be a function or not based on the original, we can use something called the horizontal line test. So if we do the horizontal line test on our original relation, we can see that it does not pass it. It passes through two different points, which means that if we were to now reflect it over the y equals x, or in other words, to find the inverse, the inverse would not be a function.